Hi guys, today we're going to learn about momentum during a collision. So last time we did a virtual lab and we looked at how if there are no forces that are from outside the system of objects we're looking at, then momentum stays constant. So if we have two objects that are undergoing a collision, hitting each other, then the total momentum is going to be the same before the collision and after the collision. And remember, momentum is a vector. So you are going to have to say, well, if one thing's going right and one thing's going left, which way is positive and which way is negative? So let's look at a practice problem for this. So let's say we have a man sitting in a canoe that is at rest. It's completely still. And the man is going to walk forward in the canoe at a certain speed, 0.5 meters per second, relative to the shore. And we want to know what happens to that canoe when he does that. So let's look at how to set up this problem. We said that the sum of the momentum of everything before anything happens is going to equal the sum of the momentum after whatever it is, whatever collision happens. Now this is kind of like a backwards collision because everything starts together and then it's actually going to move apart. So the two objects are the man and the canoe. So before, the man is still, he's stationary. The canoe is stationary. Neither one has any momentum. But then after, the man is going to move and he has momentum. And that means the canoe has to move in order to cancel out that man's momentum. So to find the momentum of the man, we look at the mass of the man times the final velocity of the man, or the velocity after this. Then we look at the mass of the canoe times the velocity of that canoe. So if we want to solve for the canoe's velocity, we want to know what this is, the velocity of the canoe afterwards. Then we're going to have to get that v by itself. So we're going to move, let's subtract the man's momentum from both sides. So if we subtract that from both sides, then the left side is going to go from being 0 to the momentum of the man, the mass of the man times his velocity. And that's going to equal the mass of the canoe times its velocity. So if we want to solve for velocity of the canoe, we divide both sides by the canoe's mass. And that leaves the velocity equal to negative mass of the man times velocity of the man divided by mass of the canoe. So if we plug in numbers there, oh gosh, what is my pen doing? VC equals negative, the mass of the man was 75 kilograms. The velocity of the man is 0.5 meters per second forward, so that's positive. Then we're going to divide by the mass of the canoe, and that's 120 kilograms. Okay, so if we plug that into a calculator, then we have negative 75 times 0.5, all divided by 120, and we should get negative 3125. So we could round that to like 3 digits is usually our best bet. So I'm going to say 313 meters per second. So that would be my final answer. So that tells us the canoe moves backward. That's what the negative sign means, at 0.313 meters per second. So slower than the man, but it's still moving. So let's try one more. We have this 5 kilogram projectile launcher, and we shoot a 209 gram, hint, hint, grams need to be converted to kilograms. So we're going to launch a 209 gram, which is 0.209 kilograms, projectile at 350 meters per second. We want to know at what velocity initially is the launcher going to recoil. So we start out the same exact way. We say the sum of the momentum of everything before equals sum of the momentum of everything after. So before, nothing's moving. Nothing has any momentum. So it's all zero. It's stationary. Then once it's launched, that projectile launcher has momentum and the projectile has momentum. So if we're trying to find the recoil velocity, the final velocity of the launcher, then we can say that negative momentum of the projectile is going to give us the momentum of the launcher afterwards. So they both cancel each other out again. So if we want to find what that is, momentum is just mass times the velocity. So the mass of the projectile times the velocity of the projectile is what we plug in for that momentum. And then same thing for the launcher. Mass of the launcher times velocity of the launcher. And then to solve for velocity of the launcher, we divide both sides by the launcher's mass, and we end up getting the velocity of the launcher is negative, again, so the projectile's mass, which is 5 kilograms, times the projectile's velocity, 350 meters per second. And then we divide all that by the mass of, oh, sorry, I did this wrong. So the projectile's mass is 0.209 grams. Ooh. See, you guys aren't here to help me out. And we divide that by the launcher's mass, which that one is 5 kilograms. Whew. So 0.209, well, negative 0.209 times 350 divided by 5 gives us 14.63. So I'm just going to round that to 14.6 meters per second. So if that thing launches and nothing's holding it back, and it doesn't have, if there were no frictional force, no air resistance, nothing, it would just start sliding backwards at 14.6 meters per second. But usually there's something behind it, or there's some form of friction. So let's move on a little bit and talk about different types of collisions we can have. So when two objects make contact with each other, so they can either start apart and then hit, or they can start together and move apart. Anytime they make contact, that's a collision. And in every single collision, we learned in our virtual lab, momentum is conserved. So in elastic collisions, we conserve momentum still. Momentum stays the same before and after. When that elasticity is 0, we always conserve momentum, but we also don't change any energy. So the kinetic energy before the collision equals the kinetic energy after the collision. So that's what makes an elastic collision special. So usually if you have the same mass objects, they end up with like the same speeds afterward. So in an inelastic collision, when you slid that bar over to 0% elasticity, we still conserved momentum. So momentum is still conserved. It's always conserved when we're looking at all the objects in the system. But here, we lose kinetic energy. And that energy turns into forms like heat and sound. And if the collision is perfectly inelastic, then the objects stick together and become one object after all. So there's no elasticity, there is no bouncing whatsoever. And after the collision, the math is a little bit easier. Since there's only one object, we only have one object's velocity with like both of the masses stuck together. They would have the same velocity. So if we look at a problem like this, we have this big fish. He's moving forward at 2 meters per second. And then he swallows the little fish, which has a significant portion of the big fish's mass. So if we want to know what's his velocity after he eats, he's got his own mass, and then he's got the little fish's mass, then we're going to set this up the same exact way. We're going to say the sum of the momentum before, so when he's just swimming, is going to equal the sum of the momentum after. So the momentum of the big fish before plus the momentum of the little fish before equals the momentum of both fish after. So before, the big fish has a mass. Now, we're not told its mass. We're told that the stationary fish has 1/3 of the big fish's mass. So if we say that that little fish has a mass of m, that means the big fish has a mass of 3 times that, 3m. So we'll just use those letters and we'll see what happens with that. So the big fish has 3m times 2 meters per second, but the little fish is stationary at first, so he doesn't have any momentum. Then afterwards, the big one's eating the little one, so the total mass would be 4m, big plus little, and we want to find this final velocity. We want to know the velocity of the big fish after his dinner. So what we get over here, actually, before we do anything else, we can look at this. Well, we can say that 6m is going to equal 4m times VF. And if we have these m's on both sides, then the m's actually cancel out. It doesn't matter what the actual mass of these fish are. Okay, so those ratios are going to be the same even if we don't know the masses. As long as one is 3 times bigger than the other, we still have the same ratio. So if we want to find VF, that's just going to be 6 divided by 4. We divide both sides by 4. And if meters per second. And if we want to put that in decimal form, we could say, well, fraction form will be 3/2, or it would simplify, or we can just say 1.5 meters per second. So that is our perfectly inelastic collision. So sometimes you can have elasticity that was in between. We also looked at situations like that in our virtual lab, but everything works the same way. The math works the same way. You're just not gonna, it just might be, you might have a little, a few more variables to deal with. But if you write it out every single time, then you're good. All right, so for the remainder of your class today, you're going to do just these first 3 pages of problems. So page 235, 6 through 10, 238, 13 through 18, and then 240, 19 through 21. You do not have to do this right now, the page 250. This will be next class. Okay, so have a fantastic day, and remember to email me or message me on Remind, whatever you need to do if you have questions. All right, bye.